And you'll notice that there's more than one question here. In fact, there are 4 questions that are part of this homework assignment. Just this one, and each of them is worth 0.25 points. And what I'd really like to do is I'd really like to cover 3 things together. Those are going to be electron geometry, hybridization. Let me move back just a tiny bit there. Electron geometry, hybridization, and bond angles. Because you'll get separate questions on all of these, and I think it'll be more helpful if we do all of these for all the examples that we do. And all 3 of these are related to the number of electron groups. And if we go one step further back, the number of electron groups is, you can only get that from the completed and correct Lewis structure. So I guess it sort of goes like this. So LS is for Lewis structure. You make the best Lewis structure, and we can even write best Lewis structure there. Then from the best Lewis structure, you determine the number of electron groups. And from there, you can determine the hybridization, the bond angles, and the electron geometry. So everything in this portion of the class goes back to doing a best Lewis structure and feeling comfortable doing that. So we'll go through this process each time. And I can do it as completely or as slowly as you would like. When I look at this molecule in the first part of homework 1, question 1, it says around each of the carbon atoms, well, there is only one carbon atom in CH2Cl2. To solve this problem, it is probably helpful to draw the Lewis structure, of course. That's what I've been saying anyway. And if you do draw the Lewis structure, you would count up the number of valence electrons. And carbon, if you remember from the periodic table, each carbon atom has 4 valence electrons. There are 2 hydrogens, and each hydrogen has 1 valence electron. There are 2 chlorines, and each chlorine has 7 valence electrons. My periodic table is around here somewhere. Nope, no luck. But remember, you look at your periodic table, and from your periodic table you can tell, holy cow. So group 17, each of these elements has 7 valence electrons. Carbon, group 14, has 4. Hydrogen, all the way over here in group 1, group 1, there it is, has 1 valence electron. All right, and then you add them all up, 14, 15, 16, 20. Then the next step for drawing a good Lewis structure is to put the least electronegative atom besides hydrogen in the center and connect it to each of the atoms with single bonds. Each of these single bonds is 2 valence electrons, so 2, 4, 6, 8 so far. Following that, the next step is to sprinkle your valence electrons around outside atoms first. Each of our hydrogens does not need any more, so I will start with one of my chlorines. I have 8, so that's going to be 10, 12, 14, 16, 18, 20. And I just so happen to have run out. If I had extra, I could consider putting them on my central atom. This is the best Lewis structure for CH2Cl2. And from there, what we get is we now look at the central atom. We see that there are 1, 2, 3, 4 electron groups around it. So, and 4 electron groups means that the electron geometry is tetrahedral. The hybridization is sp3. and the bond angles are 109.5 degrees. And these always go together. And so for this one, good, the answer is going to be tetrahedral. And next thing I'll point out is that when you look at sp3, it actually stands for an s orbital and 3 p orbitals. So this is 4 orbitals hybridizing, and that's because there are 4 electron groups. So the 4 electron groups and the 4 orbitals hybridized, that is always true. So if there are 3 electron groups, there will be 3 hybridized orbitals, and that'll be sp2, which will be 3 orbitals. Any questions about this for what's called question 1 here, but we're all still on the same homework problem. Any questions about this one? Okay. If not, then we'll move on to, well, let's see if I can keep it visible here. We'll move on to H2O. For H2O, perhaps you're familiar with its Lewis structure. It goes H, O, H, with 2 pairs of electrons around it, the center atom. We could go through the process, but I think perhaps we're familiar with this. If not, I'm happy to go over the process. Just let me know. And I guess I haven't been watching the chat, but I will now. So chat a question if you need to, or if you want to. Okay, so we have our best Lewis structure. Now we get the number of electron groups. And this is sometimes tricky, but this, so each single bond is 1 electron group. Each pair of electrons is 1 electron group. So this oxygen has 1, 2, 3, 4 electron groups, which means that it's also going to be tetrahedral. The hybridization is going to be sp3. And let me write that, and then we'll talk about the bond angle. So tetrahedral sp3. And then the thing that we have to consider here, and this is one thing that's different, is that when an oxygen has a pair of electrons, any atom has at least 1 pair of electrons around the central atom, this 109.5 degree bond angle is altered a little bit. And what I mean by that is, so if we were to, each electron, well, so let me give you the answer. The answer is less than 109.5 degrees due to the electron pair, in this case pairs, but as long as there's at least 1, this is true, due to the electron pairs repelling the atoms. And each electron pair will be a slightly slightly stronger source of electron density. And so if you have an oxygen with 2 hydrogens attached to it, and there's a pair of electrons over here, it basically takes the 2 hydrogens and squeezes them a little bit together. And this bond angle is the one that ideally in tetrahedral is 109.5, but with at least 1 electron pair becomes a little bit smaller. And we can draw the shape of this. So we can draw both of these actually while we're here. So tetrahedral, the way that I ask you to draw a tetrahedral is one of the positions straight up, and 3 of them angled a little bit down. And so what I mean is, let me fill in the spots here. So This is 4 positions around carbon for this example up here. And, excuse me, one of them goes straight up, and the other 3 are angled down a little bit. And this is what's called an out wedge, because it's coming out of the page at you. And this series of diagonal lines, which I don't know if I did very well there, it should get smaller as you go back. Let me just do a slightly better job of that. There we go. Get smaller as you go back to symbolize that this, so first off, let's call it, this is a back wedge. And that's because this chlorine is in the back of the page. The chlorine with the out wedge is in the front of the page. And at least that's how we draw it. That's how chemists draw it typically. And it's called forced perspective. Now, if we were to do it for water, it might look like this. Here's your O. Here's your 2 H's. And for electron pairs, you don't typically draw bonds, but you could draw a pair of electrons a little bigger and a pair of electrons a little smaller to occupy the 2 positions down here. And finally, what I'm saying is the hydrogen-oxygen-hydrogen bond angle is less than 109.5 due to the electron pairs pushing the bonded atoms farther away. On the other hand, the hydrogen-carbon-hydrogen bond angle is expected to be a perfect 109.5, as is the hydrogen-carbon-chlorine bond angle, and in fact, all of the bond angles in this molecule here. Are there any questions about these?